All right, time to do some probability here. My hope today is to finish talking about the crux of continuous distributions, to finish with the normal distribution, so that you will be set free to use that all-important continuous distribution. Okay, so let's get to it. Okay. So last time we were talking about the chi-squared distribution. That was the last thing we discussed. And we knew that this was related to the gamma distribution, where we took alpha to be r over 2 and beta to be 2, okay? So, that's kind of strange. It's like, why would you do that? Well, it turns out this is going to come up later on when we discuss the square of a standard normal random variable. It turns out that will actually have the chi-squared distribution with 1 degree of freedom. That R is our degrees of freedom, okay? So here's a little thing to get our minds working together here. So what are the PDF mean and variance of X if the moment generating function of X is given by that? Remember, I've kind of harped on the fact that the moment generating function is the all-important thing that tells us what distribution it is that we're dealing with. Well, hey, that moment generating function, I'm telling you, is something that we have seen before. I promise. So I have 3 over 3 minus t, 3 over 3 minus t, okay? What if I divided numerator and denominator by 3? Then that thing would become 1 over 1 minus t over 3, okay? 1 over 1 minus t over 3. And I think we've seen that before. Let me flip back here a few slides. Okay. Yeah. So remember we said it was 1 minus, or 1 over 1 minus t over 3 is what the moment generating function was. And back over there it said that t was less than 3. So this looks like we have a lambda equal to 3. We have our moment generating function. Okay, and so this thing is going to have the exponential distribution with lambda equal to 3. And of course, the expected value is going to be 1/3. Remember, that's sort of like the waiting time in a Poisson process with lambda equal to 3. So 1/3 would be our waiting time to the first observation. The variance is 1/9. And we have the CDF, the cumulative distribution function, given by 1 minus e to the negative 3x. And of course, the density is going to be 3e to the negative 3x for x equal to or greater than 0 and 0 otherwise. Because that was just kind of a problem to make sure you've been paying attention here, okay? The minute we have the moment generating function, boom, we know everything, okay? So there we go. Okay, again, just wanting to remind you yet again, if we have a Poisson process with mean lambda, that is the expected number of events in a 1-unit time interval is lambda, then the time to the first occurrence of an observation is exponential, has the exponential distribution with parameter lambda. And of course, the mean is 1 over lambda, okay? Time until the alphth occurrence has the gamma distribution with parameter alpha. And then we have this weird transition to beta, which happens to be 1 over lambda, okay? And then the time to the alpha over 2th occurrence has a chi-squared distribution with r degrees of freedom, okay? And lambda here is going to be 1/2, okay? Lambda is going to be 1/2. It's 1 over beta. Here alpha is equal to r over 2, and beta is equal to 2, okay? All right, so that's just the connection. I'm connecting the Poisson to the exponential, to the gamma, to the chi-square. They're all connected, okay? Poisson process is, we're not just horsing around here. I mean, the context in which I've placed the whole thing really is in the context of, being a traffic engineer. But you can see how that would extend to a lot of other situations. But queuing theory is really important. That's something that comes up in computer science. It has to do with waiting times, data processing. So queuing theory is a big deal. And by the way, the chi-square distribution, actually, I keep going back and forth between chi-square and chi-squared with a D at the end. It's actually the D is the proper term, but I think you'll forgive me for that. The chi-square distribution shows up when you square a so-called standard normal random variable. And if you add together any number of those, like if you take a bunch of standard normal random variables and add them together, which happens very, very often in practice, you end up getting the chi-squared with some number of degrees of freedom, okay? So that comes up in something called hypothesis testing, which if you're in probability theory, we won't do in this class, but if you're in probability and statistics, we will. Chi-square distribution helps us with something called goodness of fit. There's a chi-squared goodness of fit test. If I think that something has like the normal distribution, I can kind of graph some of the data that I've collected, and and I want to know, okay, how well does this data fit that of a normal distribution? And I can use a chi-square goodness of fit test to do that, to test that, okay? Yeah, okay, so moving on. Telephone calls arrive at a doctor's office according to a Poisson process on the average of 2 every 3 minutes. 2 every 3 minutes. Okay, so our unit time interval here is 3 minutes. Okay, so like I'm setting up this problem in such a way that you don't get hung up on the time interval always having to be 1 or something. The unit in quotation marks here is actually a 3-minute interval of time. On average, 2 every 3 minutes. 2 every 3 minutes. So if they come 2 every 3 minutes, then that means I'm in some sense getting 2/3 of a call every minute. Okay, so that's another way to think about it. Okay, but here let's let X denote the waiting time until the second call that arrives. The second call that arrives. Find the probability that that X. So X is just the waiting time in minutes until the second call that arrives. I think I'm I think I'm missing a word there. That should be after 10 a.m. Sorry about that. Okay, so I kind of start the process at 10 a.m. and I start paying attention at that point. Okay, so let X denote the waiting time until the second call that arrives after 10 a.m. Find the probability that X is bigger than 2. Okay. Well, what do you think? I'm waiting for the second observation. I'm waiting for the second observation, okay? That, my friends, is going to be the gamma distribution, okay? The gamma distribution. The gamma distribution, I'm waiting for the second observation, the second call. Okay, and what is beta? Beta is 1 over lambda, right? Lambda is, so what is lambda in this particular case? Well, lambda is 2, okay? And what is going to happen here? Here, so, okay, so lambda is 2. So what does that mean? Lambda is 2. So beta is equal to 1 over 2, okay? 1 over 2, okay, in this particular case. So let's go over and figure this out, okay? I want the probability that x is greater than 2. Okay, so the probability that x is greater than 2 equals what? And what's true about x? X is distributed as gamma, okay? The gamma distribution with alpha, I'm going to put A for alpha, with A equal to what? I'm waiting for the second observation. And what is beta? Beta is equal to 1 over lambda, okay? And so beta is equal to 1 over 2, okay? Okay, I'm waiting for the second observation, like that, okay? So what am I going to do? It's going to be equal to 1 minus the probability that x is, right? So this is going to be the probability that x is less than 2, okay? So I'm going to go gamma distribution, okay? X is 2. What's alpha? Well, it's 2. I'm waiting for the second one. What is beta? 1/2, okay? Cumulative, yes, right, so true. Okay, I'm a little bit I'm a little bit nervous about that because um, I'm thinking about the fact that our time unit was 3. I think what I want here, I mean, I'm all right, I'm just gonna kind of go back on my word here. I want to take the total length of time, and I think what I want to do is I want to say this, okay? Okay. So because alpha beta, yes, that is exactly what I want to have in this case. So the whole thing was through one time unit here was 3 minutes. If I want to talk in terms of minutes, then I really need to take that entire 3-minute interval and divide it by 2. I'm going to see 2 over that, so it's going to take me 3/2 minutes to get one interval there. Okay, because alpha times beta, which is 2 times 3 over 2, is equal to the right. Is that what I want? Right. Sorry about that. That is what I want. I want there to be. So I want 2 observations, 2 phone calls. Is the average over a 3-minute time interval. So on average, each call is going to be coming in every 1.5 minutes. Okay. So the average time it's going to take to get those 2 calls is alpha times beta. The average time it's going to take to get those 2 calls is alpha times beta, which is 3. 2 times 3 over 2 is 3 minutes. So that's what I need. I should be putting 3 over 2 in here. Okay, 3 over 2 in here. Yes, right. So the probability that x is bigger than 2, right? So that x is bigger than 2 is actually 61.5%, which is dramatically different. Okay. Okay. So and that kind of makes sense because if you think of the mean in this case, the mean number of calls in this 3-minute interval is 2, then it's entirely possible that I could end up with more than that or less than that. So it's not that surprising to have the probability be rather large that you're beyond the average, okay? That's not that weird. The thing that tipped me off to the fact that something was wrong was that the probability was teensy. And I thought, what in the world is going on here? Okay, so 61.5% is the answer there. Okay, so enough of that. Let's go back to the presentation here. Okay. Okay. And we are at the normal distribution. Yeehaw. Here we go. Okay. So here's the deal. The density for the normal random variable is given by that amazing formula. Okay. That amazing formula right there. Okay. And what's so amazing about that is that you know, it has the number pi in it. It has a square root of 2. There's just some fascinating things going on. And the fact that that even integrates to 1 is sort of miraculous in and of itself. That actually takes a fair amount of work to do that. You have to do some like multivariable calculus to pull that off. So the parameters given here are mu and sigma. And of course, mu is just the mean, and sigma is the standard deviation, okay? So sigma squared is the variance, okay? The other thing that's true is, here's a graph of the density right here. This is a graph of the density. It turns out that sigma is the distance from the mean over, right? So sigma is the standard deviation. Sigma is the distance from the mean over to an inflection point. An inflection point is a place where this graph goes from concave down to concave up. Okay, so one standard deviation to the left or the right from the mean is going to give you a point at which the density changes concavity from concave up to concave down, or concave down in this case over here to concave up. Okay, so so mu plus sigma, mu minus sigma, those are inflection points for this thing. It's pretty clear that this graph of the density is symmetric about the mean. That is, I mean, you can kind of see that everything is measured. X is measured in terms of its difference with the mean, and you square that by 2 sigma squared. So, I mean, X being some distance to the right of the mean will give the same function value as X being some distance to the left of the mean. Okay, so this thing is symmetric about the mean. Okay, that is the bell-shaped, so-called bell-shaped curve. The first person to kind of mess with this a little bit was someone by the name of Carl Friedrich Gauss. Okay, he's a German mathematician. He's actually on, you can go look this up on Google, but he's actually on the 10 Deutschmark bill. There's a picture of his face, and a picture of this curve is on there, and even this formula is actually on there. In fact, hey, why don't you know, let's go. I'll show you. Okay, so let's go look at that. I think that would be kind of a fun thing to do. So we go in here. Let's see. Let's talk about so Gauss. So Deutschmark picture. There he is, right there. Okay, let's see if we can get a little clearer viewing. There it is. Do you see it? That is remarkable. There's the bell-shaped curve right there, and you can see the density of the normal random variable sitting right there. Okay, Carl Friedrich Gauss, amazing mathematician. Okay, so let's go back to the presentation here. Okay, so here we are. We have our density. Okay, I promise that thing integrates to 1. I'm not going to do it. I'm not going to prove that just because that would involve some pretty highbrow techniques. But you know, if you're interested, you know, you can ask me about that later. It's definitely a very cool proof for sure. Okay, so there's the normal random variable, the bell-shaped curve. Okay, the notation is kind of a you know, fancy looking n. I just usually write, you know, a normal a normal n, and then you put mu, comma, and then sigma squared. So that's how you notate the normal random variable, with mean, mu, and variance sigma squared. And if you go through the rigmarole of trying to find the moment generating function, you know, that is, you would go over here, you would multiply this density by e to the tx. You would combine things under the same exponent. You would integrate from negative infinity to infinity. And lo and behold, eventually you kind of shift things around and you end up with this as the moment generating function. Of course, if you take the derivative of this, it's just going to be itself times the quantity mu plus sigma squared t. Okay. So again, if you take the derivative of this, I would kind of challenge you to do this. It would be itself times the quantity mu plus, okay, what's the derivative of this? The 2 comes down, plus sigma squared t. So if I plug in 0, well, this guy right here is going to become 1, and the thing that's multiplying it in parentheses, that would just be mu, and I would get mu as the mean. Duh. We're not surprised by that. This thing had better deliver mu as the mean because that's what we said it was. Similarly, I'm telling you, if you go through the process of taking the second derivative of this and plugging in 0 and subtracting off mu squared, you're going to end up with sigma squared, okay, the variance. Once you have the moment generating function, you have everything. The normal distribution with mean 0 and standard deviation 1 is called the standard normal distribution. Standard normal distribution. This is very important because you know, there are infinitely many normal distributions. I could have any mean, I could have any variance. So there are infinitely many normal distributions. So the standard normal is basically a way of turning every normal random variable into the standard normal. So what you want to do is kind of remove the unit dependence and get it in the standard normal form. And we'll talk about that, how to do that later, how to convert any normal random variable to standard normal. That is something that you can actually accomplish. Okay, so you don't have to deal with infinitely many possible normal distributions. Okay, standard normal random variables denoted by Z, and the PDF of Z, all you do is you just use this PDF, right? The density, you just put mu equal to 0 and sigma equal to 1, okay? And that sort of simplifies this thing to this. And this thing gets a special notation. This is the Greek letter phi, and usually you use Z to remind you that Z always reminds you that we're talking about the standard normal. We're talking about the standard normal random variable. So there is the density. By the way, what would the moment generating function of this thing be? I think it would be kind of silly. Okay, so like mu is 0, so this would go away completely, and sigma is 1. So the moment generating function is just 1e to the 1/2 t squared for the standard normal. Okay, for the standard normal. Okay, so one reason you want to convert a given normal random variable to the standard normal, which we'll talk about, is then I can kind of describe probabilities in terms of just one normal distribution, namely the standard normal. And here's the notation for the cumulative distribution function of the standard normal. You use capital phi, okay? Capital phi of Z, okay? You know, most times you use capital F. Phi is like the Greek for F, okay? So this is so special. The normal random variable is on this, you know, upper echelon of continuous distributions, in fact, of all distributions. And so it gets a special letter that everybody recognizes. So capital phi of Z is the probability that capital Z is equal to or less than Z. This is the CDF. It's just the integral from -infinity to Z of little phi of y dy, right? I'm using a different variable for the integration in here. Okay, so I'm integrating this guy all the way up to little z to get this thing. So what do I get when I do that? Well, I get this shaded area right here. Yeah, so this is the shaded area, and this right here is the standard normal curve. Notice how it's centered at 0. Of course, the standard deviation is 1. So if I went down to -1 or up to +1, I would be at an inflection point on this curve, okay? So anytime we see capital phi of z floating around, you know, we know that we're talking about the CDF for the standard normal, and little phi of y or whatever, that we're talking about the density of the standard normal random variable, okay, with mean 0 and standard deviation 1. Now, this picture right here, before we get into that next slide, this picture right here is all over the place on the web, and it's even in your books. Okay, so for instance, there is a picture in the theory of probability text on page 190. But they don't necessarily draw the picture and tell you exactly what's going on. But what they have is essentially a table where you can look up various little z values, and it will give you the area corresponding to little z values if you look up the proper z thing using the corresponding row and column. Okay, it gives you the corresponding area. So there's a table that does that. And the same thing is true for the prob and stats people. There's in the back of your book, table 5A and 5B give you, and they actually draw a picture for you in there of what it is they're giving you. They have all these different probabilities listed back there in those tables in the back of the book. And incidentally, you may or may not be aware of this, but for both classes, in the front, inside the front cover and inside the back cover. Inside the front cover, they have a summary of all the discrete distributions. Inside the back cover, they have a summary of all the continuous ones. So that's kind of a nice thing to have it at your disposal. But again, table 5A and 5B for the prob and stats book, page 190, there's some summaries of various area values for this given right there. The table's fairly intuitive. So I'm not going to actually use the table. I'm actually going to use Excel to do some of these things. So find the probability that capital Z is equal to or less than 1.52. All right, let's do it. Capital Z is less than 1.52. So let's go over into Excel. Okay, so this is, I want the probability that Z is less than or equal to 1.52, okay, is less than or equal to 1.52. Okay, well, you're going to go equals normal. Okay, if you start typing normal, there's normal standard distribution right here. Yeah, okay, that's the standard one. Here's a normal. You can even do normal distribution for any mean in variance, but normal standard distribution is right here. So what's the z value? 1.52. And do I want cumulative? Well, yes, I do actually. Okay, so that's 93.6% basically. And I guess that makes sense, right? Because remember, the standard normal, 0 is right in the middle. So 50% of the data will be to the left of 0. So for z to be less than 1.52, 1.52 is clearly to the right of 0. You know, that's one standard deviation is at 1, because the standard deviation is 1. So I'm 1.52. So think about this. This standard normal, 1.52 means 1.52 standard deviations to the right of the mean, because 1 is 1 standard deviation. 2 is 2 standard deviations for the standard normal, because 0 is right in the middle and the standard deviation is 1. So 1.52 means I'm 1.52 standard deviations to the right. So I'm past that inflection point. So it makes sense that there would be 93.5% of the data to the left of this thing. Okay. Going back here. So what else do we have? What's the probability that Z is trapped between negative 2.48 and 1.52? Well, that's not really all that different. Negative 2.48 negative 2.48. So now I want the probability that negative 2.48 is less than or equal to, by the way, it's not really important that it's less than or equal to, it's less than or equal to z. It could be less than or equal to 1.52. Okay, well, that's going to be equal to normal standard distribution, 1.52. Yes, cumulative, minus normal standard distribution, negative 2.481. Okay. And the reason this isn't really all that much smaller than the other one, but is because negative 2.48, that's really pretty far to the left of 0. So that's going to be barely subtracting anything off, you know, just from the left tail of the standard normal distribution. Negative 2.48 means negative 2.48 standard deviations to the left of the mean. Okay. So not surprising, it's not all that different. Okay, what's the third one? Find the probability that z in absolute value. Remember, z has 0 as the mean, and so it can be negative or it's negative or positive with equal probability. The standard deviation is 1 in both directions. Okay, probability that z in absolute value is less than 2.5. Okay, that z in absolute value is less than 2.5. Okay. Well, let's see. Okay. Probability that z in absolute value is less than, was it less than? Was it less than? Let's see. Yeah, less than. Okay, fine. Okay. Z is less than 2.5. Okay. Well, that's the same thing as the probability. Look, that means that negative 2.5 is less than z is less than 2.5. Yeah. Okay, that means that z has to be trapped between negative 2.5 and 2.5. Okay, so what is that? That's going to be equal to the normal standard distribution. Normal standard distribution. Okay, 2.5. True. Yeah. Minus normal standard distribution. Okay, negative 2.5. 1. Okay, so it's 98.7% of the data, 98.7% of the data. Okay, and by the way, the normal distribution has some very nice symmetry that you can oftentimes take advantage of. So one thing that you could have done to do this problem, watch, you could have computed the probability that z is greater than 2.5, okay, which by the way is 1 minus the probability that z is less than 2.5. Right? I'm not really worried about equals. Okay, so this, I could have gone equals 1 minus normal standard distribution. 1 minus, okay, so 2.51, okay. And then, so I get 0.06, that's the probability that 0.00621, that's the probability that z is bigger than 2.5. So that's how much area is to the right of 2.5. So if I want the area between, between negative 2.5 and 2.5, I know that there's 0.00621 in the right tail, and there's that same amount in the left tail. So really this thing up here should be equal to 1 minus 2 of these, because there are 2 tails with this amount that I want to get rid of. So when I hit enter, this should be the same, and it is. So there's some nice symmetry that you can take full advantage of with this stuff. Okay, find a C such that the CDF is equal to that. Now that, that's like a that's like a percentile rank. So I'm looking for the basically the 98.38 percentile in this particular case. How can I do that? Well, you could use the tables by trying to sort of look up a number that is that. So like if I look in this thing, 0.9838, I see it in the text. 0.9838 is in both of your texts, and it corresponds to a C value of 2.14. 2.14. So 0.9838, yes, in both texts corresponds to 2.14 is the C value that should work. 2.14, okay? But look, I can actually find that in Excel also, okay? So if I go over to here, okay, so I want the probability that Z is less than C. I want this to be equal to 0.9838. Yeah, 0.9838. Okay, so how do I find that? So what is C, right? So C equals what? Well, watch this. You go equals normal standard inverse. Here it returns the inverse of the standard normal cumulative distribution. It gives you, what you're going to input is a probability, and it will return the value that delivers that. Okay, remember I said 2.14 was what it should be. So what's the probability we want? 0.9838. There is 2.14. Yeah, so C is equal to 2.14 basically. Okay. All right. Back to the presentation. Okay. Find a C such that that happens. Okay, C such that the probability that 0 is equal to or less than Z is less than C is 0.291. 0.291. Let's think about that together. 0.291. So I want the probability that 0 is less than Z is less than C. I want this to be equal to 0.291. Well, do you see? Okay, so let me actually. Okay, I'll leave it as C. Do you know? Okay, well, how much area is to the left of 0 for the standard normal? Well, 50%. So this means that the probability that Z itself is less than C would have to be equal to 0.5 plus 0.291, which is equal to 0.791. Okay, so so what is the C value? Well, I'm going to go equals normal standard inverse, and I put 0.791 in there, and I get I get 0.8099, right? So C equals 0.81 basically. I'll just put 0.81. Okay. And indeed, you could check it out if you want. Equals normal standard distribution. Okay, if I put 0.81 in here and I say, yes, I want the cumulative, I get 0.791, which is exactly what we would expect. Yeah, 0.791, just so you know. Okay. And let's have a look-see at some of these other exercises. I want the 21th, the 21th percentile of the standard normal. What does that mean? That means I want a value such that 21% is to the left of it. Yeah, 21%. 21% is to the left of it. Okay, and the 95th percentile. Okay, the 95th percentile. Okay, the 21st percentile and the 95th percentile. So let's see here. I want the probability that Z is less than C sub 21, I think is C sub 0.21. Okay, that's kind of how we were writing these things before. Okay, this needs to be equal to 0.21. Yeah. So how would I find it? Well, I would go normal, standard inverse. Okay. 0.21. And I get negative 0.806, right? So C sub 0.21 equals negative 0.81, basically. or 0.8, I'll do 0.806. Okay, 0.806. Okay, so the probability, I mean, you can check it out here, right? Equals normal standard distribution. What if I put, I'll just select this thing like this. Oops, I want to put 1 for cumulative. And indeed, I get 21%. Okay, what about the 95th percentile? Okay, probability that Z is less than C sub 0.95 should be equal to 0.95, 95%. And what do we get? Well, you go equals normal standard inverse. And by the way, you can do this in your table as well by just searching for a number, sort of a percentage that corresponds to what you want, or using symmetry of some kind in there. Normal standard inverse, okay, 0.95, and I get 1.64. So C, 1.645. C, okay, C sub 0.95 equals 1.645. Okay, so that means if I get 1.645 standard deviations to the right of the mean, I'm going to have encountered basically 95% of the data. 95% of the data. On the other hand, this other guy over here, what this is saying is, if I am negative 0.8, basically negative 0.81 standard deviations to the left of the mean, 0, then I basically have 21% of the data to the left of that. Okay? Yeah. So that's some nice little exercises with the standard normal. If X has the standard normal distribution with mean mu and standard deviation sigma, then what happens if I take X and I subtract the mean? Well, if the mean was mu before, if I subtract, so if the mean's 100 and I subtract 100 from everything, what's the new mean going to be? Well, 0, okay? Okay, and what if I were to divide that by the standard deviation? Well, the standard deviation before was sigma. If I divide by sigma, the new standard deviation will be 1. So if I take X, which is a normal with mean mu and standard deviation sigma, I subtract the mean and I divide by the standard deviation, I will get a standard normal random variable. Standard normal. This is called scaling the thing. Let's think about this. Think about what the units are. So suppose like X was originally in dollars. If I subtract the mean, still in dollars. If I divide by the standard deviation, that's also in dollars. Dollars, they cancel. The dollars cancel and you have a unitless quantity. Unitless. So when I take X, I subtract the mean and scale it by the standard deviation, what I'm basically doing is getting rid of the units and putting it in this one world of standard normal distribution that is unitless. Unitless. Okay, so these are often referred to as the z-score for X, right? Z-scores is something that we convert things to. This is called normalizing the data. Okay, so that no matter how obnoxiously huge my numbers are, if I subtract the mean and divide by the standard deviation, it puts it in this one world of the standard normal distribution. The standard normal distribution. Okay. I think I think that I'm probably going to, I think I'm going to stop for now. I might come back a little bit later and add a little bit, but I think I'm going to go ahead and stop this for now at this point. Just know this is a nice little conclusion. The fact that we can take any normal random variable, we can subtract the mean and divide by the standard deviation, and the thing is normalized at that point. Okay. That is all for now.